So, dear students, I welcome you for understanding the chemical reactor designing, in which today we are going to talk related to the multiple reactions. Now, when we consider the multiple reactions that is taking place, in that the different type of chemical reactions that is taking place, that is consecutive reactions, series reactions, parallel reactions, complex reactions, all these reactions are being carried out there in a reactor system. However, it's economic success that depends on the desired reaction. That means what is required, the aim of production, that depends on the economics for the production of that particular reaction. And for that purpose, we have to understand the different aspects of temperature, pressure, concentration, the type of the reactor, the secondary reactions that are taking place. All these things has to be studied, has to be understood, has to be analyzed, and has to be optimized to give you the desired production. So this desired production, when you talk, it is with a certain specific aim, and that aim should be fulfilled. For that, you have to understand the complete reaction and complete kinetics of the different aspects of that reaction system, reaction mix. उसमें क्या क्या हो रहा है वो सारी चीजें समझनी पड़ेगी. And then this rate factor, that is also important, the time factor, that is also important. At minimum time, you should get the maximum concentration of the desired product. This is the ultimate economics. At minimum time, you should get the maximum concentration of the desired product. So with keeping this aim in the mind, we have to understand, we have to analyze the different situations from kinetic aspects, from reactions, type of the reactor. All these things has to be analyzed. So it is the key factor in the economic success of any chemical plant is the minimization of the undesired side reactions that occur along with the desired reaction. So desired reaction is our basic thing, and what is our second aim? To minimize the undesired side reactions. So we are going to discuss the reactor selection, that is one aspect, and the different types of reactions, that is the multiple reactions, is the series reactions, parallel reactions, independent reaction, and the complex reaction. These are the different types of reactions that are occurring at any time in the system. So next, we have to define certain selectivity parameter. Why selectivity parameter that is coming into the picture? When we talk the different types of the reactions that is taking place in a system, when we think that the different types of the reactions that is taking place or occurring in a reaction, simultaneously the different reactions are carried out. It is not only the single reaction which is in progress at a single time. There can be the multiple reactions. There can be, not necessarily always. But reversible reactions are also taking place. So some or the other reactions that is always being carried out in the system. Out of that, the series reactions, parallel reactions, independent reactions, and complex reactions, they are more of concern. And from these different side products, the required or the selective or the desired reaction, which is important, and understanding and analyzing for optimizing the maximum production of this desired react product or desired reaction, only the desired product is obtained from the desired reaction. So selectivity parameter is very, very important. So we will discuss first the different types of the reactions, then the selectivity parameters, and then we will go into the details of how to optimize or how to get the maximum concentration of the desired product for different situations like your series reactors or parallel reactions. Then minimize the unwanted side reactions by proper choice of operating conditions and reactor selection. This is the only thing you can manage, you can manipulate, that is to operating conditions and the reactor selection. But if you go into the industry, then changing a reactor or selecting a reactor, that is difficult because it involves the maximum cost. However, you can play with these operating conditions very conveniently, and you can go on doing trial and error with your understanding and with your analysis of the particular kinetics and the reactions and the side reactions. So if there are certain situations, you will go into the industry and you can face certain situation that today I am not getting the desired product. What must be the probable reasons? Or I want to increase the production, rate of production with the same vessel. Capacity तो same है, but मेरे को production increase करने का है. That is also possible by manipulating the operating conditions to a certain extent. This is very, very tricky. For that purpose, you should be able to understand the kinetics. तो CRE का इम्पोर्टेंस यही है कि आपको डिजायर्ड प्रोडक्शन मिलने चाहिए with minimum time and with optimized conditions of to increase the economy. So with this introduction, we will switch over to basic definitions. There are four basic types of multiple reactions, that is series, parallel, complex and independent reactions. Now these types of multiple reactions can occur by themselves, in pair or in together. That means single reactions can occur, pairing of the reactions can take place, or can occur together also. So when there is a combination of parallel and series reactions, they are often referred to as the complex reaction. It's a combination of parallel and series reactions. That is called a complex reaction. So series reactions, the name itself talk about the series. A giving you B, giving you C, giving you D. That is what a series reaction is. Now what a parallel reaction? A giving you B, A giving you C. So this is what a parallel reaction. Now if it is in combination, that is A giving you B and this B is giving you C and D. So it's a combination of series and parallel reactions. कहां से क्या मिल रहा है? That is more important. Now the parallel reactions, also called as the competing reactions. These parallel reactions, they are also called as competing reactions. So parallel reactions are the reactions where the reactant is consumed by two different reaction pathways to form the different products. That means A giving you B and A giving you C. How it is going to give you B and how it is going to give you C? That is, there are different pathways, two different reaction paths. पाथ अलग अलग हैं, इसके कारण ही आपको अलग अलग प्रोडक्ट्स मिल रहे हैं. You will reach to the different destinations whenever there are different paths, and these paths can be controlled with the operating conditions. you have to manipulate the values of K1 and K2 to get the desired product. So what are the different examples now? An example of an industrially significant parallel reaction is the oxidation of ethylene to ethylene oxide. So this is what your ethylene plus oxygen giving you the ethylene oxide, or it can also burn. That again depends on the temperature and the operating conditions and the stoichiometric ratios. All this is going to decide which product you will get. How I want to control, how I can manipulate the desired product. In this case, I want the ethylene oxide. I don't want this CO2. This reaction should be prevented. And for that purpose only we are going to study the chemical reactor designing. Chemical reaction engineering is the only purpose to optimize the maximum production of the desired product. So then series reactions. क्या है series reactions? They are also called as consecutive reactions. They are also called as consecutive, one by one, consecutive. And these parallel reactions, they are called the competing reactions. No? So competing reactions, A is more competent or C is more competent? B is more competent or C is more competent? Competitively production. That is what? It's a competitive reaction. Parallel reactions, they are also called as competitive reaction. A से मेरे को B भी मिल रहा है और C भी मिल रहा है. But desired क्या है? That is all dependent on my operating conditions. So किसको प्रमोट करने का है, किसको कॉम्पिटेटिव बनाने का है, किसकी सिलेक्टिविटी ज्यादा चाहिए मेरे को, that I have to decide and control by my operating conditions. Next is series reactions. They are also called as consecutive reactions, where the reactant forms an intermediate product which reacts further to form the another product, which further reacts to form the another product. In this case, my product can be B or my product can be C also. It is not necessary that my product is always the C. My product can be B also. For this, the example is ethylene oxide with the ammonia to form the mono, di and triethanol amine, right? So ethylene oxide plus ammonia, that is going to give you the monoethanol amine, diethanol amine or triethanol amine. Now what is the desired one? Again, that depends on your market and how I am going to control it. Now in this case, in the recent years, the shift has been towards the production of diethanol amine as the desired product rather than the triethanol amine. So B is your more concerned product, that is diethanol amine, and not this C, that is triethanol amine. Then there are complex reactions. Are the multiple reactions that involve a combination of both series and parallel reactions, that involve the combination of series as well as parallel reactions. So A plus B giving you C plus D and A plus C giving you the E. So this is, but if it's A plus B giving you C plus D and A plus B giving you E and F, then it can be a parallel reaction. So it's a series reaction. Series reaction, C that is produced, and this C reacts with the A or this C reacts with the B, that is going to give you the E, or it can be the D also that can react with A or B. D also can react with A or B to produce the certain desired product. So it's a combination of series and parallel reactions. An example of combination of parallel and series reaction is the formation of butadiene from ethanol. This is your ethanol giving you C2H4. Then this ethanol that is giving you the aldehyde, and this aldehyde plus this product C2H4 that is going to give you the butadiene C4H6. Then the independent reactions. These are the reactions that occur at the same time, but the products, non-reactants, react with themselves or with the one another. So this product or the reactants, they doesn't react with each other. They're independent reactions. Even though you are taking the product reactant with maximum purity, there can be certain impurities in certain proportion 0.01001, whatever it may be. Now in general case we talk that 99% is your product pure reactant that is available for the reaction. However, it may contain 1% or 0.1% or 0.01%, and this 0.1, 0.01% that may change and that may affect your product pattern also. So in general case, certain industry prefers the same raw material company that is also the same. They doesn't switch over. If they want to switch over, they do it with the trial and error only. Then this cracking of the crude oil to form the gasoline, where two main reactions that is taking place. C15H32 that is going to give you C12H26 plus C3H6, and this C8H18 that is going to give you C6. They are independent products. That means the crude oil contains C15 also and C8 also, all the C1 to C3 different products that is available in the crude oil. So the different reactions that takes place, the cracking reaction that is going to take place depending on how much number of C's and how much number of the H that is available. Then the desired and the undesired reactions. It is a particular interest or the reactants that are consumed in the form of the desired product D and the formation of the undesired product U. In a competing or side reaction, in the parallel reaction sequence, it is a giving you D and A giving you U, or in a series reactions A giving you D and this D giving you U. इथे आपण parallel reaction consider केलेली आहे and a series reaction, whatever it may be the case. We want a desired product. We want to understand the desired product. We want to minimize D is our desired product and U is our undesired product, and minimize the formation of D, maximize the formation of the D, because the greater the amount of the undesired product that is formed, the greater the cost of separating the undesired product. The separation cost, that is the major cost in our production system, that is the separation cost. And for that only we are going to understand the mass transfer and other aspects. Then we want to minimize the formation of the U and maximize the formation of the D because of the greater the amount. So this reactor system, after production, it goes to a separator. This is what a general situation everywhere or every industry. Initially certain raw materials are available. These raw materials are to be processed or are to be brought to the certain specific temperature and pressure conditions, or they are to be mixed, or they are to be conveyed to the desired mixing tanks. So this is the prerequisites before going to the reactor system. So main reaction is taking place in a reactor system, and after the reaction that is taken place, then you are going to separate the products. You will get the different products. You will get C, you will get D, you will get U. So these are to be separated. That is what you require the other chemical engineering aspects. So in a highly efficient and costly reactor scheme in which very little of the undesired product U is formed in the reactor, because the cost of separating is more, you want to minimize the cost of separation. For that purpose, you can increase the cost of the reactor system, or you can increase the cost of designing, so that you will get the maximum desired product. If a reactor scheme is inexpensive and inefficient, resulting in the formation of substantial amount of the U, the cost of the separation system could be quite high. Normally, as the cost of the reactor system increases in an attempt to minimize the U, the cost of separating the species U from the D decreases. Okay. Then what is selectivity? Selectivity is of more concern. One product is favored over the another when we have multiple reactions. So out of these multiple reactions, what is my desired product? In this case, the D is my desired product with respect to the U. So I can define this selectivity as rate of formation of D to the rate of formation of U. Now it's a ratio of rate of formation of D and rate of formation of U. When I am talking the rate term, when I am talking the rate term, in terms of rate term, it is called as the instantaneous selectivity. It is called as the instantaneous selectivity. The rate term, when it is incorporated, it is called as the instantaneous selectivity. Now rate, that is dC minus RA, which is equal to dCA upon dt, minus RA, which is equal to dCA upon dt, and this dCA upon dt incorporates the time factor. Time factor, that means the concentration at any time dC upon dt. This T factor, that means it is changing with your time, changing with concentration. This concentration that changes with time, dC upon dt, that means the change in concentration with respect to time. So this concentration, when it is changing with respect to time, it's a function of that particular instant. It is at that particular instant. When we talk at that particular instant, and that is why it is called as the instantaneous selectivity. That is why this rate of formation of D to the rate of formation of U, दोनों का भी rate जहाँ पे of formation of D and U is there, then it is called the instantaneous selectivity. Why? Rate term incorporates your dC upon dt. This concentration is a function of time. When this concentration is going to change with respect to time, that is what, at that particular time, this is the concentration, this is the rate. So it is the instantaneous selectivity. The next is the overall selectivity. Next is the overall selectivity. Now, what is overall selectivity? Overall selectivity, it incorporates the molar flow rate, molar flow rates, or the amounts, or the amounts. When it's a continuous reactor, it will be the molar flow rate. Continuously inlet and outlet that is there. So whatever the number of moles that is going out from the reactor system, so it is the molar flow rate of the desired product, D in this case, upon the molar flow rate of the undesired product, U in this case. This is what? The overall selectivity. This is incorporated with this S sign of the desired product upon the undesired product. This is the molar flow rate of the desired product upon molar flow rate of the undesired product. So selectivity used in the current literature, D in this book, that is the Fogler, they're representing with this S, and above that the approximation sign that is there. That is the overall selectivity. For batch reactor, the overall selectivity is given in terms of number of moles of D and U. So this is the number of moles of D and number of moles of the U. In case of a continuous reactor, that is it's a molar flow rate. Continuous reactor, it's a molar flow rate. And in a batch reactor, it is the number of moles that is to be considered. Because in a production continuous, it's a continuous output you will get. However, in case of a batch reactor, you are getting whatever the number of moles that is available finally. You are not taking out the product continuously. Now, comparing the overall and instantaneous series, instantaneous selectivity for a CSTR. Overall and the instantaneous selectivity, and so develop the relationship between SDU and S bar DU for CSTR. So A giving you the D and A giving you the U. The SDU, that is what is your instantaneous selectivity, right? SDU is your instantaneous selectivity. It incorporates the rate term, or whenever there is a rate term, it's an instantaneous selectivity. And when there is a molar flow rate, then it's a overall selectivity. This is instantaneous, this is overall selectivity. So the mole balance on the D for FD, which is equal to RD into the V, and the mole balance on the U, FU, which is equal to RU into V. Then substituting for FD and FU in this ratio of overall selectivity, we will get RdV upon RuV, which is equal to RD upon RU, which is nothing but the SDU for. Consequently, for CSTR, the overall and instantaneous selectivity are equal, and that is nothing but RD upon RU. This is the situation for CSTR. Then what is the yield? Yield is the second terminology that is to be considered. Like the selectivity has two definitions, one based on the ratio of reaction rates and one based on the ratio of molar flow rate. Based on the reaction rate, that is the instantaneous, and based on the molar rate, that is the overall selectivity. In first case, the yield at a point can be defined as a ratio of reaction rate of a given product to the reaction rate of the key reactant. It's the ratio of product to the key reactant. Key reactant, that is more important. So yield at a point is defined as the ratio of reaction rate of a given product to the reaction rate of the key reactant. Means yield is the output upon the input. Output क्या है? The product D, desired product D. Input क्या है? A, that is what a reactant. So the rate of production of D upon the rate of consumption of A, that is what the yield is. So the yield at a point can be defined as the ratio of reaction rate of a given product to the reaction rate of a key reactant. This is sometimes referred to as the instantaneous yield. So again, when you talk related to the rates of the product to the rate of reactants, it becomes your instantaneous yield. And second, in the case of reaction yield based on the molar flow rate, the overall yield is defined as the ratio of moles of product formed at the end of reaction to the number of moles of the key reactant A that has been consumed. So कितने प्रोड्यूस्ड हुए हैं और कितने डी प्रोड्यूस्ड हुए हैं और कितने नंबर ऑफ मोल्स ए कंज्यूम हुए हैं. That is the moles of the product formed at the end of reaction. This is nothing but the ND. ND is nothing but the moles of the product formed at the end of a reaction. Moles of the product formed at the end of reaction. This is nothing but your ND. And the number of moles of the product of the key reactant A that has been consumed. Consumed कितने हो रहे? So how that can be calculated? Na0, that is initially कितने हैं और finally कितने बचे हुए हैं. Na is at that instant finally. So कितने consume हुए? Na0 initially कितने थे और कितने बचे हुए हैं? That is what you will get what is consumed. So this consumed moles, that is calculated as Na0 minus Na. This is what the consumption of A that is taking place. Consumption of A. Na0 minus Na. Initially कितने थे और finally कितने बचे हुए? तो उसके बीच में का जो difference आएगा, that is what is consumed. So it is nothing but your overall yield. This is the overall yield. So there is an instantaneous yield. This instantaneous yield talks about the rate term, and this overall yield that talks about the number of moles of the product formed at the end of a reaction and number of moles of the key reactant A that has been consumed. Okay. So this is for a batch system. Batch system, you are going to take the number of moles, and for a batch system, you are going to calculate the number of moles. And in a continuous reactor system, you are going to calculate the flow rate. You are going to calculate the flow rate. इट्स अ कंटिन्यूअस है तो टाइम के साथ वो चेंज होगा ही होगा. कंटिन्यूअस जो भी चीज है, जो भी फ्लो रेट मिलेगा आपको, दैट हैज टू चेंज विथ योर टाइम. सो इट्स अ फंक्शन ऑफ टाइम, एंड दैट इज व्हाई इट्स अ flow rate. FD is nothing but the number of molar flow rate, and ND is the moles of the product formed at the end of reaction, and FD is the molar flow rate. इथे वरती आपण पाहिले. Now coming to the consecutive reactions. There are also the reactions in series. Now we will see what should be the maximum production of the R. So coming to the consecutive reactions, that is nothing but the reactions in series. A giving you R giving you S, where the rate constants are K1 and K2 for A giving you R, and K2 for R giving you S. Now the writing a rate equation for the first, that is A giving you R. What rate equation you are going to write? That is minus RA, which is equal to minus dCA upon dt, which is equal to K1 into the Ca. K1 into the concentration of Ca. That is what? Rate of production of R. So minus Ra, which is equal to D minus dCA upon dt, decrease in the concentration of A, which is nothing but K1 Ca. Rr is the rate of formation of the reactant R, which is nothing but the dCr upon dt. Now here R, that is produced from first reaction, and it is being consumed by the second reaction. So we can write K1Ca, which is getting produced, minus K2Cr, minus K2Cr. Then for Rs, rate of production of the S, which is equal to dCs upon dt, which is equal to K2 into Cr. एक ही रिएक्शन से चेंज हो रहा है, that is R giving you the S. So the initial concentration of A is Ca0, and for the rate expression, it can be written as minus ln Ca upon Ca0, which is equal to Kt. This is for the first order reaction. Ca, which is equal to Ca0 into e raised to minus K1T. I hope you remember all these initial derivations. Then according to law of conservation of mass, that is Ca, which is equal to Ca plus Cr plus Cs. Ca0 इनिशियली जितने हैं उतने प्रोड्यूस्ड हो रहे हैं. दैट इज व्हाट. Ca कितना है बचा हुआ फाइनली, Cr कितना प्रोड्यूस हुआ है, Cs कितना प्रोड्यूस हुआ है. So that is nothing but next is the manipulation. So to determine the concentration of R, that is nothing but Cr at different time, it is necessary to integrate this above equation. Now it's a simplification. So this dCr upon dt, which is equal to K2Cr, which is equal to K1 Ca0 e raised to minus K1 T. This is nothing but you are writing with this equation dCr upon dt, which is equal to K1 Ca minus K2 Cr. This Ca, this is obtained from this Ca, which is equal to Ca0 e raised to minus K1 T. And the same thing is there. So this is a first order linear differential equation similar to dy by dx plus py, which is equal to which is equal to q. So integration factor that is there, e raised to integral of p dx, which is equal to q e raised to integral of p dx plus I. So by using this integration factor method, you have to simplify it, this process. Integration factor that is coming as I, which is equal to minus K1 Ca0 upon K2 minus K1, and with this further simplification, so this Cr that is coming as K1 Ca0 upon K2 minus K1 into e raised to minus K1 T minus e raised to minus K2 T. This is what is obtained as your Cr. So we have solved this equation, first order linear differential equation, by using the integration factor method, and you get this as your reaction. I know you can understand the mathematics, how to solve the linear differential equation, and you can do the things. That is given here. Now, the next thing is that to get the maximum value of the R. How to get the maximum value of the R? So Cr max. Okay. So this Ca0, which is equal to Ca plus Cr plus Cs, and this Cs you can calculate as Ca0 minus Ca. Ca0 initial number, what is the concentration of A that is there, Ca, which is equal to the Ca0 into bracket Ca0 into e raised to minus K1 T, Ch value A, then Cr you are having this value. So you know Ca0, you know Ca, you know Cr. So you can calculate the value of Cs by substituting all these Ca and Cr from the above equations. So after simplification, we will get Cs as Ca0 into 1 minus e raised to minus K1 T. This is condition if K1 is very large as compared to the K2 is very large as compared to the K1. So K1 is the deciding factor because K2 is very large, and if the K1 is very large as compared to the K2, then your Cs, which is equal to Ca0 1 minus e raised to minus K2T. You can simplify this for these two conditions. So this is what the rate of formation of S. Cs is nothing but the rate of formation of S, that is determined by the reaction rate constant K1, and the rate of formation of the Cs, which is determined by the rate constant K2. When K1 is very large as compared to the K2, K1 large है, तो जो smaller factor है K2, that is going to decide the kinetics. First है the continuous production, first production होऊन जातं. The slowest step is your rate determining step. Slowest step is your rate determining step. So this is of more concern. The slowest step, that is nothing but the rate determining step. That is why rate of formation of the Cs, rate of formation of the S is dependent on your K2 kinetics for the second reaction. Indicates that the rate of formation of S is determined by the reaction rate constant K1, that is by the first step of two-step reactions. Indicates that the rate of this second equation indicates that the rate of formation of S, that is governed by the reaction rate constant K2, which is the slower step in the two-step reaction. Slowest step that is going to decide the rate. The values of the reaction rate constant K1 and K2 can be utilized to determine the time at which the concentration of intermediate product R is maximum. भी क्या करने का है मेरे को? When the concentration of R that should be maximum. I have to calculate that because my R is the desired product, not S. So when I am thinking R is my desired product, then what should be the R, maximum R? And how I can calculate this? I have to differentiate the concentration of R with respect to time. It is going to vary with respect to time. It is going to change with respect to time. And that is why I have to differentiate it. So I have to differentiate this CR equation. So I have to differentiate this CR equation with respect to the time. Differentiating this equation with respect to the time. That is going to give me the CR maximum. That is going to give me the CR maximum. That is the concentration, maximum concentration. So dCr upon dt, which is equal to 0, differentiating that you will get this thing. With the further simplification, the time at which the maximum concentration of R occurs is nothing but the Tmax. The time at which maximum concentration occurs is nothing but your Tmax. So by simplifying this, you will get this term as the 0. This term as the 0. So this can be equated. This is K1 e raised to K1 Tmax, which is nothing but K2 e raised to minus K2 Tmax. For further simplification, you will get Tmax as the ln K2 upon K2 minus K1. So you will get this as your T maximum. That depends only on the K values, the rate values, rate ratio of the K1 and K2. So this is the, now to obtain the CR maximum, we have calculated the T maximum value. T maximum जब मिलेगा मेरे को तभी CR maximum मिलेगा. So CR maximum I am going to substitute as CR maximum and T as a T maximum. So same equation, K1 Ca0 upon K2 minus K1 into e raised to minus K1 T. Now K1 T, T will become the T maximum. So I have substituted this T as the T maximum. Here also T as your T maximum. So after simplification, I get K2 upon K1 raised to K1 upon K2 plus K1. So finally I will get CR maximum upon Ca0, which is equal to K2 upon K1 raised to minus K2 upon K2 minus K1. So general question that can be asked, that how I can calculate the concentration of R. How I can calculate the concentration of R in a series reaction where R is my intermediate product. Then second question, how I can calculate the concentration of a undesired product in a series reaction, A giving you R giving you S. Next, how I can calculate the maximum time at which the concentration of R is maximum. So this is what the T maximum. So complete derivation आएगा इसमें. And how I can calculate the CR maximum, that is what should be the maximum concentration of the desired product. So you can solve all the CR maximum. Then a graph that is to be plotted. This is the CR maximum, that is what the concentration, and against the T maximum. So this graph is showing the three lines, each is for its own concentration. A concentration. What will happen to A concentration? A that is getting continuously decreasing, Ca. So Ca0 initially, that is maximum, so it is continuously decreasing. A that is continuously decreasing. Then what is happening to A giving you R? What is happening for the R? So R initially 0 है. R initially 0 है because there is no R and S, only A that is available in the reactants. So maximum concentration of A, 0 concentration of R and S. So the graph will start from 0 for R. So R will initially increase, that is the first reaction is taking place, A giving you R. And simultaneously at the same time some production of the S that has been started. At initial values, some production of the S that has been started. So it will start with a certain delay. Formation of the S that will start with a certain delay. पहले तो R form होगा and after some time the formation of the S that will takes place. So R will continuously increase and the CS will also increase. But I want my desired product is the R. So what will be the maximum R at a T maximum, and the corresponding CR is CR maximum. So T maximum that can be obtained from my rate constants. रेट कॉन्स्टेंट्स के ऊपर डिपेंडेंट है, ln k2 अपॉन k1 अपॉन k2 माइनस k1. यहां से मेरे को T मैक्सिमम मिल जाएगा and for that corresponding T maximum I can calculate the CR maximum. Now consider our two cases when k1 equals to k2 for consecutive reaction, that is dCr upon dt, which is equal to k1 Ca minus k2 Cr. So K2 which is equal to the K1. So I have substituted that K1 Ca0 e raised to minus K1 T. Let's simplify केलं. I will get dt d upon dt Cr e raised to minus K1 T, which is equal to K1 Ca0. Then calculating the integration factor and I will get the calculation of CR. CR which is equal to K1 Ca0 T e raised to minus K1 T. So this is what the value of CR, but which case? It is the case when K1 which is equal to the K2. This is the case for CR for K1 which is equal to the K2. General case, CR that is calculated as this one. And if you will simplify this, K1 equals to KT, you will get the same equation. Now special case 2, that is when Ca upon Ca0 and the ratio of reaction rate constants are specified for a consecutive reaction K1 and K2. So alpha, which is equal to Ca upon Ca0, and capital K is defined as K2 upon K1, and beta, which is defined as Cr upon Ca0, capital gamma, that is defined as Cs upon Ca0. Ca, you know, Ca0 into e raised to minus K1t, alpha, that is coming as e raised to minus tau, then beta is coming like this, gamma is coming like this. Now the next thing is the condition for the desired product. So we have calculated the Cr maximum and the T maximum in a consecutive or series reaction. Now we are going to calculate the conditions for the desired product. What should be the temperature? What should be the pressure? Condition means temperature, pressure, concentration conditions. Here we will talk related to the temperature conditions. That is, consider again simple reaction A giving you B giving you C as the reactant, and B is the desired product, or R is our desired product, C is the undesired product, that is nothing but the S is the undesired product or the waste product. Now it is depending on your activation energy, what is nothing but your rate constants K. K is function of the activation energy E. So activation energy of second reaction is higher than the first reaction. That is E2 is greater than E1. Activation energy for second reaction is greater than the first reaction. Then what will be the temperature in the reactor, or what should be the temperature profile in the reactor? So when E2 that is greater than E1, then a higher temperature in a reactor produces more C, because E2 ज़्यादा है. So I will get higher C if the temperature is high. This is more important. E2 ज़्यादा है तो एनर्जी में ज़्यादा सप्लाई कर रहा हूं, तो क्या होगा, मेरा कन्वर्शन B2C विल बी फास्ट. So my this graph जो यहां से चालू हो रहा है ऐसे, वो इधर से चालू हो जाएगा. Instead of starting from this point, it will start from this point if when E2 is high, activation energy is high. E2, that is the activation energy for second reaction, is high, and temperature is high in the reactor, then this is going to produce more C. Now it is therefore necessary that at the end of a reaction time, when the concentration of component B is high, the temperature must be low. यानी जैसे जैसे B प्रोड्यूस्ड हो रहा है वैसे वैसे मेरे को टेम्परेचर कम करने का है, रिएक्शन वेसल का टेम्परेचर कम करने का है. B जैसे प्रोड्यूस हो गया वैसे टेम्परेचर मेरे को कम करने का है. So B जैसे जैसे produced हो रहा है, this is for the B that is getting produced. And if the higher temperature, this is CB, concentration of B. And depending on the temperature, the concentration of C is going to vary. If it's a higher temperature, then C will have this graph. If I will reduce the temperature, then I can delay this production of the C. So, by using this understanding of activation energy, which is nothing but depending on your kinetics K constant, so at the beginning of a reaction, when the concentration of B is low, the temperature needs to be high. At the beginning of a reaction, means initially part, यहाँ पे B का concentration कम है, B बहुत ज्यादा जनरेट नहीं हुआ है इनिशियली, तो वहां पे मेरे को B इंक्रीज करने के लिए टेम्परेचर तो इंक्रीज करना पड़ेगा. बट ज्यादा जब टेम्परेचर इंक्रीज करूंगा तो जैसे जैसे B बनेगा वैसे वैसे C भी बनना चालू हो जाएगा, बिकॉज द एक्टिवेशन सफिशिएंट एनर्जी इज देयर. सो B will get converted into C. So to reduce that, I am going to reduce the temperature of B. So therefore, little concentration of C results in a very little. Thus, whenever there is E2 that is greater than E1, there needs to be a falling temperature gradient along the axis of a reactor. So as the B that is produced, I have to decrease the temperature in the reactor system. I have to decrease the temperature in the reactor system. For that purpose, I am using such a plug flow reactor. You must have studied the certain heat exchangers or the plug flow reactors, where your inlet temperature is high. Here initially it's a higher temperature that is available, and the B formation will be maximum in this region. As the B moves up, I have to decrease its temperature, so that I am going to restrict or reduce this second reaction. I am going to restrict or reduce this second reaction as the B that is produced. C तो मेरे को रिस्ट्रिक्ट करने का है. So जैसे जैसे B बन जाएगा मेरे को, वैसे वैसे मैं टेम्परेचर उसका कम कर दूंगा. So that टेम्परेचर कम करूंगा, that means B to C conversion that will be reduced. So टेम्परेचर प्रोफाइल इनिशियली तो मेरे को हाई रखना पड़ेगा, बट जैसे जैसे लेंथ ऑफ द रिएक्टर इंक्रीजेस, वैसे वैसे मेरे को टेम्परेचर रिड्यूस करना पड़ेगा, so that B will not get converted into C. That is what the temperature profiles should be available into the reactor system. This is what we have talked in terms of kinetics, and we have reached to a conclusion how I can control the temperature in a reactor system. This is very important, and this is very desired when you talk related to the productions. Production तो चलता है, but how I can optimize this production, how I can increase the rate of production, how I can maximize the production, there you need the kinetics. बिना kinetics के काम नहीं होगा वहां पे. सारा केमिकल इंजीनियरिंग फेल ठहर जाएगा unless and until you have understanding of this kinetics. So this is how the temperature profile should be in a reactor. That depends on your kinetic aspects. अपन ने क्या स्टडी किया? कंसेक्यूटिव रिएक्शन स्टडी किया, उसका मैक्सिमम कॉन्सेंट्रेशन ऑफ बी के लिए क्या कंडीशन है वो स्टडी किया, एंड depending on that, depending on the activation energies E2 and E1, how the temperature profile should be, that we have decided, and vice versa, the temperature conditions will be there when E2 is greater than when E1 is greater than E2. So this is most important thing to understand. मैं काइनेटिक्स क्यों स्टडी कर रहा हूं? तो काइनेटिक्स मेरे को इसके लिए स्टडी करने का है कि टेम्परेचर क्या रखने का है मेरे को रिएक्टर सिस्टम में, एंड हाउ आई कैन मैक्सिमाइज the production, how I can maximize the rate of production and rate of the desired product, yield of the desired product, the selectivity of the desired product, how I can play with that, temperature, pressure and concentration, ये तीन ही चीजें हैं. This is what we have talked in the last year also, temperature, pressure, concentration and flow rates. So when you talk in kinetics, it's a concentration that is more concerned. Now, search for a temperature profile. So what will be the temperature profile? It is also possible to study the optimum temperature profile by searching for the minimum process time at which the maximum yield of CBM or CRM of the product can be obtained. The same thing that is written, that is dCA upon dt, which is equal to K1CA, dCB upon dt, which is equal to K1CA minus K2CB. A basic equations, I hope you understand them. Then the component B is of interest and its concentration CB is considered as an independent variable. The reaction time T and the concentration of the feed component A are considered as the function of the concentration of B, that is CB. Such representation does not give rise to multi-valued function if the value of the CB is considered upon the maximum. The next is the irreversible parallel reactions. We are considering the parallel reactions. First, we have talked related to the series reactions. Now we will talk related to the parallel reactions. The reactants, same reactant, the product are different. A giving you B, A giving you C, or A plus B giving you L, A plus B giving you M. The reactants are consumed by two different reaction pathways. This is more important. Two different reaction pathways are available to react, and both are having the different activation energies and different rate constants. The reaction in which the reactants are not common in all the pathways are called the concurrent reactions. Reactants are not common, that is more concerned. Reactants are not common. यहाँ पे B है, A plus B है, यहाँ पे A plus A है. Are not common in the pathway are called the concurrent reactions. So example we have already talked. This is ethylene plus ethylene oxide, that is giving you CO2 plus H2 and ethylene oxide. It is what the ethylene oxide is our desired production. Then again these are the examples. Now coming to the kinetic aspects. Nitration mixture. For reaction, say generalized reaction, A giving you B and A giving you C, having the rate constants K1 and K2. The reaction is considered to be the first order in each step. So I can write the rate equation, which is equal to minus RA, which is equal to minus dCA upon dt, which is equal to K1CA plus K2CA. That is what concentration of A at that instant. That depends on both the reactions. Now the concentration of B, that depends on the one rate constant, that is K1CA. Similarly, I can write for RC, which is equal to dCC upon dt, which is equal to K2CA. For reactions on integration, it can be written as your minus ln Ca upon Ca0, which is equal to K1 plus K2T. This is what we already studied. Then by dividing, so the rate of B to the rate of C, which is nothing but dCB upon dt upon dCC upon dt, which is nothing but K1CA upon K2CA. So CA cancel, you will get the K1 upon K2. And by integrating this, you will get CB minus CB0 upon CC minus CC0, which is equal to K1 upon K2. So I can plot a graph for this corresponding to this, that is the two equations ln Ca upon Ca0 against T. This is what my equation minus ln Ca upon Ca0, which is equal to K1 plus K2T. So I have plotted a graph of minus ln Ca upon Ca0 on the y-axis against the T on the x-axis. So the slope y, which is equal to mx, which is equal to the mx. So m is nothing but your K1 plus K2. So this is what my slope is, K1 plus K2. The second equation is CB minus CB0 upon CC minus CC0, which is equal to K1 upon K2. So I have plotted a graph of CB against the CC. CB against the CC. So this will have a slope of K1 upon K2. So this is what the two equations we have plotted, that is, this is minus ln Ca upon Ca0, which is equal to K1 plus K2 into T, and this is CB minus CB0 upon CC minus CC0 against K1 upon K2. From there, these two slopes, you can calculate the values of K1 and K2. From these two slopes, you can calculate the values of K1 and K2. Once the K1 and K2 and K1 plus K2 are known, the values of K1 and K2 can be calculated from the above graphs, right? Now the concentration time curve relationship between the three components A, B and C involved in the parallel reactions can be plotted as we have plotted previously for series reactions. This is for the parallel reactions. That is, C is the concentration of A and C is the general concentration. It can be for A, it can be for B, it can be for C, against the time. So A concentration initially, that is maximum. B and C concentration, that is 0 at initial. So there is no product that is available. B and C, they are 0. And only A that is available. So Ca0 is maximum. So as the reaction proceeds, A giving you B or A giving you C, so we will consider higher the activation energy of the B that is there. So this reaction is going to give you the more product. Now the selectivity in such reactions can be determined the ratio of rate of formation of B and C. In the question of selectivity that comes, we already talked about the selectivity, overall selectivity and instantaneous selectivity. Instantaneous selectivity is related to the rate terms, rate of formation of B to the rate of formation of the C, and overall selectivity is the exit molar flow rate or the number of moles at the end of a reaction for the desired product B to the undesired product C. When the reaction order is same, in such reactions it can be written as this is minus dCB upon dCA, which is equal to. Now this is the second derivation. For instantaneous reaction, there is a mixed order case. That is, one is a first order reaction and second is the second order reaction and the first order reaction. So what will be the rate constants and the other things that will be there?